biggest eruptions, the coldest temperatures, and the largest oceans in the solar system. They're all on moons.
There are moons with ice volcanoes. There are moons with lakes of methane and methane rainfall, smog, clouds, moons that are so volcanically active that they keep remaking their surface, moons with all kinds of plumes shooting off into space. Really a much wider range of environments than we ever could have imagined.
Often when I'm describing to the general public or even to my fellow scientists these moons of Saturn and Jupiter, I call them worlds because they really do have the complexity and mystery of a whole world.
Jupiter and Saturn have over 60 moons each. These giant gas planets and their moons are like mini solar systems. And each moon has a distinct personality. Iapetus, a two-toned moon in black and white. Titan, with a dense orange atmosphere. And icy Enceladus, blasting ice geysers 200 miles into space. Each moon is unique. But they all have one thing in common. All moons are natural satellites, held in place by gravity. But moons do more than just go around planets. They help stabilize the planets in their orbits and keep the machinery of the solar system running smoothly.
The diversity of moons is an interesting combination of predictable laws of science and then complete randomness of just things smashing together and the chips kind of falling where they did in a way that you could never predict.
Planets and moons begin the same way. Once a star turns on, there's a lot of dust and gas left over. Slowly, the dust particles clump together, forming rocks. The rocks smash into each other and form boulders. Slowly, the objects get bigger and bigger. The process is called accretion.
One can think of it as forming a snowball and rolling it down a hill. As it rolls down the hill, it collects and gathers up yet more snow, which makes it roll faster and harder. And so that process of runaway accretion actually happens in the formation of the planets and in the formation of moons as well.
It sounds simple enough, but nobody knew for sure how it worked. Until 2003. On the International Space Station, astronaut Don Pettit was experimenting in zero gravity. He put grains of salt and sugar inside a plastic baggie. Instead of floating apart, they began to clump together. This is how both planets and moons build up. But instead of taking shape around stars, most big moons take shape around planets. If the same process makes them all, what makes all of them so different from each other? Take two of Jupiter's moons, Callisto and Ganymede. Two very different moons, each born from the same debris when Jupiter was still young. Ganymede formed close to Jupiter, where there was lots of debris. Because there was so much material, it came together quickly, in about 10,000 years. And it was hot. The heat separated the ice from the rock. You can still see it in Ganymede's distinct landscape.
The primary factor that affects why moons are the way they are today is energy. How much energy was put into them as heat during accretion, and how much energy has been lost. All of those factors go into telling us why moons behave the way they do and why they look the way they do today.
Callisto's surface tells a different story. It formed much farther out, where there was less debris and less heat. It took longer and cooled faster. Unlike Ganymede, Callisto's surface is uniform. Rock and ice never separated. Where a moon forms can also mean the difference between survival and destruction. Get too close, and a planet's gravity will rip a moon to shreds. Scientists believe this is what happened to many moons when Jupiter was young.
And it's very likely that Jupiter had an entire conveyor belt of large moons that were wanting to form, only to be swallowed up by the planet itself. The large moons we see today are only the last ones that were able to stabilize right at the end of that process, stop their death spiral, and survive into the position we see today.
But Jupiter keeps trying to eat them. The gravity of the giant planet reaches out and pulls hard on the orbiting moons. It transforms them from lifeless balls of rock into strange and dramatic worlds. Jupiter is the largest planet in our solar system. It has 63 moons. The 4 largest are called the Galilean moons, named after the astronomer Galileo, who discovered them in 1610. They show how gravity controls both what moons look like and how they behave. The first of the Galilean moons, Io, orbits closest to the planet, just 260,000 miles above Jupiter. That's about the same distance as our moon is from Earth. But unlike our moon, the surface of Io has no impact craters. Scientists realized that meant the surface was new. But how could that be?
Every time you look at Io with a spacecraft or even with a telescope, it's a little bit different. So the geology on Io changes like the weather on other planets. It's that active.
When NASA first sent probes to fly past Io, they were shocked. They saw dozens of active volcanoes. This is footage of an erupting supervolcano on Io, blasting 200 miles into space. Everyone had the same question. How could there be active volcanoes on a moon? The answer was simple: gravity. Jupiter's gravity is so huge that it reaches out and crunches the moon. And it's not just Jupiter's gravity pulling on Io. Other nearby moons also pull on it as they pass by. So, the core of the moon is being worked back and forth all the time. It's called tidal friction and generates extreme heat in Io's core.
Almost like bending a wire coat hanger until it breaks and you feel the inside of the coat hanger there. It feels rather warm. That tidal friction, that internal friction, heats the interior of Io until it's become actually one of the most volcanically active worlds in the solar system.
The constant pushing and pulling generates temperatures thousands of degrees high inside Io. It blasts out in gigantic eruptions of lava.
Io is the prime example of tidal forces and gravitational interactions in the solar system. It is constantly being pulled by Jupiter, and it's constantly getting pulled by the other moons as well. And so as a result, there's a tremendous amount of heat created.
The floods of erupting lava constantly resurface Io, which is why there are no visible impact craters on this moon. Gravity also heats Io's neighbor, Europa. Europa's orbit is farther away from Jupiter, so it's much colder. Instead of lava, the surface of Europa is ice. The lowest recorded temperature in Antarctica is minus 128 degrees. Europa's surface is twice as cold. But underneath all the ice, there may be an ocean of water heated by the same tidal friction that makes Io volcanic.
Europa has a subsurface ocean, almost certainly, and that subsurface ocean is in contact with the rocky mantle, which provides heat and also provides probably appropriate nutrients to sustain life.
Someday, we'll send a probe to explore beneath the ice on Europa. And maybe we'll discover life forms living there in warm European oceans. Out beyond Io and Europa are nearly 60 more moons. They orbit much further away from Jupiter, where the effects of the giant planet's gravity are much weaker. Out here, it's too weak to generate tidal friction and heat the moons. So, these remote worlds are cold and barren. But not featureless. They bear the scars of countless collisions, and scientists believe it was collisions that created the most extraordinary moon system of them all. The planet with the most unusual moon system is Saturn. It's spread out over more than 200,000 miles. Technically, there are more than 1 billion moons. That's right, 1 billion moons. And altogether, they make up Saturn's rings. A moon can be a hunk of rock or ice, no bigger than a pebble, as long as it orbits a planet. The rings of Saturn are made of countless pieces of rock and ice. They go from the size of a pebble up to the size of a city.
We don't refer to all the ring particles that can get to be as big as 10 or 20 meters across. We don't refer to them as individual moons, but when we find a body that is maybe 1 kilometer or 2 across, then you can start talking about it as a moon or a moonlet.
Saturn's rings are one of the oldest mysteries of astronomy. Where did they come from? To try and find out, NASA sent the Cassini probe on a 12-year mission to study Saturn, its rings, and its moons.
We took, with Cassini, probably the most beautiful picture that's ever been taken, and I'm not the only one who has said this. Cassini was in the shadow of Saturn, cast by the sun, and so you don't see the sun, you see the backlit planet of Saturn and its beautiful rings. You see the refracted image of the sun poking out from the side of Saturn, and nestled in all of that splendor is the small little dot.
That tiny dot is not a moon. That is the distant planet Earth, nearly 1 billion miles away. Most of what we know about Saturn, of its rings and moons, comes from Cassini. Before Cassini, we thought there were only 8 rings. Today, we can see over 30.
What we have found at Saturn has been just literally an embarrassment of riches. We're seeing something that we had seen before, but now we're seeing it with a level of detail and clarity that was just mind-blowing.
Scientists used to think the rings were made of the icy leftovers after Saturn was formed, about 4 billion years ago. But anything that old should be covered with cosmic dust and dirty. So, why do Saturn's rings appear bright and clean, almost new? To get the answer, Mission Control maneuvered Cassini close to the rings. The probe saw that all the ice pieces in the rings are constantly colliding and breaking up. And each collision exposes new surfaces that are clean and polished. This is what astronomers think happened. When Saturn was young, it had no rings, just lots of moons. At some point, an icy comet zoomed in from deep space and smashed into one of those moons. The comet broke up into billions of pieces. The impact also pushed the moon closer to Saturn, where the planet's enormous gravity broke it up. Now, debris from the moon and ice from the comet mixed. Gradually, Saturn's gravity pulled all those fragments into rings around it. The story of moons is the story of gravity. Gravity holds them in orbit. It heats up their insides and shapes their surfaces. In the end, it controls everything about moons, even their survival and destruction. Gravity can even create new moons by kidnapping asteroids, comets, and even whole planets. We know that gravity makes moons. The standard way is to assemble them from debris left over when planets are formed. But gravity makes moons a second way too. It captures them. Imagine a wandering comet or asteroid. Somehow, it gets knocked off course. It wanders too close to a planet. Gravity acts like a science fiction tractor beam and grabs it. Not quite enough gravity, and it escapes. Too much gravity, and it collides with the planet. Just enough, and the comet or asteroid goes into orbit around the planet and becomes a new moon. Mars has two tiny moons named Phobos and Deimos. Both are captured asteroids. One is pushing outward as it circles the planet and will eventually break free and continue on its journey through space. The other is circling inwards, a little closer to Mars all the time. Eventually, it'll smash into it. This is Cruithne. It's an asteroid, really, just 3 miles across. But it's sometimes described as Earth's second moon.
With the little object Cruithne, which was discovered back in 1986, we start to get into this realm of what does it mean to be a moon?
Only a few thousand years ago, Cruithne was an ordinary asteroid, orbiting the sun like billions of others. But eventually, it wobbled out of its orbit in the asteroid belt and got snagged by Earth's gravity. But then, Cruithne did something unusual. Instead of orbiting around the Earth like a normal moon, Cruithne began to follow behind it.
And so one might call that a sort of a moon of the Earth. Not exactly, though, because that object is on, it's on its own independent orbit around the sun, not the Earth.
Sometimes asteroids capture their own moons. In 1993, the Galileo spacecraft flew past the asteroid Ida and found something nobody expected: a tiny, half-mile wide moon.
The fact that we saw a satellite around only the second asteroid ever to be encountered with a spacecraft immediately tells us that moons around asteroids must be incredibly common.
Not all captured moons are small. The mother of all captured moons is Triton. It orbits the planet Neptune, and it is big. About 1,700 miles in diameter. But Triton is a moon with an unusual story.
Triton was a very puzzling problem for planetary scientists because our traditional view would tend to make all the moons orbit in the same direction that the planet itself spins. In the case of Triton around Neptune, it's the other way around. Neptune is spinning this way, Triton is orbiting around in the opposite direction.
This means it didn't form like most moons, out of the debris left over from the birth of the planet. Or it would orbit in the same direction. So something wasn't right.
Triton is huge. And its orbit is funny, it's anomalous. It does not seem as though it formed as a part of the Neptune system. It seems much more like a captured planet.
Scientists now think Triton was once a dwarf planet, like Pluto, and a giant planet like Neptune certainly has enough gravity to capture a moon the size of Triton.
Triton was almost certainly formed way out in the outer solar system, and then at some point was captured by Neptune. Perhaps Triton early on had its own moon. They both were captured, and then that moon was destroyed during the capture process.
But Triton is in danger. Neptune is dragging it closer and closer. Eventually, it will get too close, and Neptune's immense gravity will tear it apart. Triton, the moon, will be reborn as a ring system around the planet. But what about our moon? How did it get there? Was it captured? The truth is even more extraordinary. It was born in extreme violence. Our moon, like a lot of moons, is rocky, barren, and pockmarked with craters. But in one way, our moon is unique in the solar system. For a long time, astronomers thought the moon formed from debris left over from the birth of the Earth. But researchers in the 1960s came up with a radically different idea. They suggested it came from a giant impact.
When we first had the idea of forming the moon from a giant impact, that was not a terribly popular idea. And I actually did have good science friends, colleagues coming to me saying, you know, we really have to exhaust all the slow evolutionary theories before we start talking about cataclysms.
The evidence Bill Hartmann needed was on the moon itself. And the proof had to wait until Apollo astronauts finally went there in 1969. They brought back hundreds of pounds of moon rocks. Scientists analyzed the rocks and were amazed. They were identical to rocks in the Earth's crust, and they'd been superheated. So how did pieces of the Earth's crust become super hot and wind up on the moon? Hartmann was pretty sure he knew.
This whole idea was that the Earth forms, now you hit it with something, you blow all this light rocky material off the top, that material goes into orbit and makes the moon. The moon's just made out of rocky debris.
Imagine our chaotic solar system 4.5 billion years ago. The young Earth is just one of 100 or so new planets orbiting the sun. One of them is a Mars-sized planet called Theia, and it's on a collision course with Earth. They smash into each other at many thousands of miles an hour. Theia is destroyed, and Earth barely survives. The impact blasts billions of tons of debris into space. The Earth's gravity pulls it into orbit around the planet. Now, these hunks of leftover Earth clump together and form our moon. That's the theory, anyway. But how do you test it for real? Here at NASA's Vertical Gun Range, they're recreating that ancient collision in a lab. This 30-foot-long gun fires a tiny projectile at 18,000 miles an hour. The projectile is Theia. This ball represents the Earth. By changing the angle of Theia's impact, the team can figure out how precise the ancient collision had to be in order to make the moon. In the first shot, Theia hits the top of the Earth with a glancing blow.
So here's the Earth, if you will, just suspended in space, and now it's gotten hit. So now we see the planet, the ejecta, is being ripped out of the Earth and is forming this giant impact basin. And if this really were the Earth, this basin would be thousands of kilometers, thousands of miles across.
In this simulation, Theia only skims off the surface of the planet, and very little debris is thrown out into space. Not nearly enough to build our moon. The second shot is a head-on collision.
Pow! That's the end of planet Earth. It's gone. Some of the debris is going to go out of the solar system. Some of the debris will reaccrete to form small planetesimals within the solar system.
There's no Earth left, so there's no gravity to gather the debris and form the moon. Now, the gun is set to just the right angle, halfway between a glancing blow and a direct hit.
So we'll see what happens if the Earth barely survives. Oh, gorgeous. Oh my gosh. Kapow! Now we have the entire part of the Earth being ripped apart, but the vapor plume is, oh my gosh. Jeez! That is gorgeous. But this was the beginning of our moon.
The experiment shows that Theia could have smashed into the Earth and formed the moon. But the collision had to be just right, and lucky for us, it was. Today, the moon orbits 250,000 miles from Earth. But when it first formed, the moon orbited just 15,000 miles above the Earth's surface.
500 million years after the moon formed, if we looked up in the sky, the moon would have comprised a tremendous portion of the sky. It would have been enormous because the moon would have been much closer.
Back then, the Earth was rotating so fast, a day lasted just 6 hours. But the moon was so close, its gravity acted like a brake. It slowed our planet down until a day now lasts 24 hours. The moon's gravity also created giant tides that surged across the planet, churning up the seas, mixing minerals and nutrients. This created the primordial soup from which the first forms of life arose. Without our moon, life on Earth may never have happened. And there may be other moons with a link to life as well. Moons may be the great biology experiments of the universe, the true laboratories of life itself. Moons are full of surprises. There are moons with giant volcanoes, moons with vast oceans sealed under thick ice. And now, we know a few are rich in organic compounds. In the right combination, they might even support life.
In our solar system, the biological window through which we can understand the rest of the universe may be through these moons of the outer solar system. That may be where we find our second genesis. And that second genesis is really our first deep understanding of the biological nature of the universe.
At first glance, moons don't look ideal for life. Take Enceladus. It's a shiny ball of ice, 300 miles across, orbiting Saturn.
It's the brightest object in the solar system. It reflects 100% of the light that hits it, so it's super bright, and that's because it's water ice.
In 2005, the Cassini probe spotted ice volcanoes erupting from the surface of Enceladus. That meant there had to be heat under all that ice, heat that created oceans of water. And where there's water, there's the possibility of life.
So this is Beehive Geyser here in Yellowstone, and it is shooting water vapor and water about 150 feet into the sky, and it's pretty incredible. So now imagine if you're on the surface of Enceladus. You would see geysers that look a lot like this, and they are shooting ice grains and water vapor into space thousands of times higher than this geyser here.
The ice volcanoes are powered by gravity. Here's how. Saturn's gravity works on the core of the moon, heating it up. The underground water expands and forces its way up through cracks in the surface ice and blasts out into space as ice crystals. These are some of the most spectacular eruptions in our solar system. They make Beehive Geyser look like a squirt gun. From the ice in the volcanoes, scientists have detected salt and simple organic compounds. That means the water under the ice is not only warm, but full of nutrients. Sound familiar? Heat, water, and nutrients. That's how life on Earth began.
We realized you could have all the things that we associate with oceans on the Earth going on inside a moon. It's the discovery of a lifetime.
Saturn's Enceladus has an ocean. So does Jupiter's Europa. But these aren't the only moons where life could emerge. Saturn has another moon, Titan, with an even greater potential for life. In 2005, Cassini sent a probe called Huygens on a one-way mission to Titan. For just 3.5 hours, Huygens transmitted live pictures from the hostile surface, nearly 1 billion miles away. Then, the battery died.
It was just incredible. This was the first time humans had ever touched this moon with something of our own making. It was just an event that should have been celebrated the world over. We should have had ticker tape parades in every major city across the US and Europe to celebrate this. It was that history-making and that astonishing.
Raindrops on Titan are twice as big as raindrops on Earth. But the rain isn't water. It's methane. On Earth, methane is a gas, but on Titan, it's a liquid because the moon is so cold.
There may be methane icebergs, there's certainly methane lakes and rivers, and there's methane rain and methane clouds, and maybe bugs swimming in methane.
Bugs living in liquid methane may sound unbelievable. But scientists have discovered that Enceladus, Europa, and Titan are all covered with a substance called tholin. Tholin contains the chemical building blocks for life to begin. So, could life emerge on any or all of these moons? We can't get our hands on the tholin from the moons, so Chris McKay makes it in the lab. He zaps a mixture of gases found on Titan with electricity. What he gets is a reddish-brown mud.
So this is what we make, tholin, this sort of non-biological organic material. It's produced by chemical energy put into simple molecules like methane and nitrogen, and here we got it. And that's the material we see on Titan. We see evidence for something like this on Enceladus. We see it on the surface of many of the moons in the outer solar system. This is nature's recipe for making the stuff that life eventually emerges from.
Somewhere in the outer reaches of our solar system, on some remote moon, life may have already emerged. But it probably won't be life as we know it.
Life 2.0 doesn't necessarily have to have the same genetics as life 1.0, right? In fact, the more different it is, the more interesting it is.
Whether it's the same or very different, the discovery of life on the moons of our solar system will change the way we look at the universe.
I think that should we ever find that life had originated not once, but twice in our solar system, then you can easily dismiss any arguments that say that life is unique to the Earth.
Moons are small, but they're still diverse and dynamic worlds. They help us understand how the universe works. They're essential cogs in the cosmic machine. Without any moons, our solar system would be a very different place. Without our moon, life may never have evolved on Earth. And who knows, when and if we find new life somewhere else in the universe, its home may not be another planet at all. It might be a moon.